Session 5.4, two topics today. Topic 1, integrating even and odd functions. Topic 2, average function value. Take a review about even and odd functions. For details, you can have a look at section 1.1. Now, even function. If the graph of a function is symmetric about the y-axis, then the function is called an even function. Here we have an even function. Its graph is symmetric about the y-axis. That is, if you reflect the whole graph across the y-axis, the whole graph is unchanged, symmetric about the y-axis. Then, without plotting the graph of a function, how to know the function is an even function? Have a check with this equation. Negative x and x are 2 points symmetric about the origin. If a curve is symmetric about the y-axis, the curve should have the same height at these 2 points. So when this equation holds for an arbitrary x, the function is an even function. Now, odd function. If the graph of a function is symmetric about the origin, then the function is called an odd function, symmetric about the origin. Here, this graph is symmetric about the origin. If you rotate this curve 180 degrees about the origin, the curve is unchanged, symmetric about the origin. Again, without plotting the graph of a function, how to know the function is an odd function? Have a check with this equation. Negative x and x are points symmetric about the origin. If a curve is symmetric about the origin, then the curve should have the same height at these 2 points. But the height, the heights at these 2 points have different directions. Say at x, suppose the height is positive direction, then at negative x, the height should be in the negative direction. This is a review about even function and odd functions. For details, I refer you to section 1.1. Now, topic number 1, integrating even and odd functions. In this topic, there is one figure. If you plot diagrams, then it's easy to understand the statements in this figure. Okay, now statement A. If a function is an even function, then integral from negative a to a on the function is equal to 2 times the integral from 0 to a. Integral from negative a to a is the net area of the region between negative a, and between the graph of the function and x-axis. Negative integral from 0 to a is the net area of the region between 0 and a and between the graph of the function and x-axis. Integral from negative a to a is the net area of the shaded region in the red color here. And the integral from 0 to a is the red area of the region in the blue color here. Clearly, the red area of the red region is twice the red area of the blue region because the graph is symmetric about the y-axis. Statement B, number 2. If a function is an odd function, then the integral from -a to a on the function is 0. This integral is the red area of this shaded region. Net area of the shaded region is area that lies above x-axis minus the area that lies below x-axis. Because the curve is symmetric about the origin, area above is equal to area below. So the net area above minus area below is 0. Therefore, this integral is 0 when the function is an odd function. Here is one example about integrating even and odd functions. Use symmetry to evaluate the following integrals. We have 4 integrals to evaluate. Consider this integral first. The function in this integral is 5 sine of x. This function is an odd function because this function satisfies this equation. Here on this line, I demonstrate how the function satisfies this equation. And also in this figure, I plot the graph of the function. Okay, now this integral is the net area of the region between the graph of the function and the x-axis and between negative pi over 2 and positive pi over 2. The region is the shaded region here. About this region, the area above the x-axis is this area. And the area below the x-axis is this area. Clearly, these two areas are equal. So therefore, the net area of this shaded region is 0. So this integral is 0. So the answer to question A is 0. Because the function in this integral is simple, it is easy to find antiderivative for it. So for the integral in A, we can use fundamental theorem to compute this integral. Okay, now let me compute this integral by fundamental theorem. Antiderivative is -5 cosine of x. By fundamental theorem, this integral is equal to antiderivative plot the upper limit in x minus plot the lower limit in x. That is this number. Calculator. This number is 0. So by fundamental theorem, we can verify that this integral is indeed 0. Now, the integral in B, the function is quite complicated this time, okay? So if you want to use fundamental theorem to compute this integral, you need to find antiderivative for this function. It is difficult to find one anti-derivative for this function. Okay, but anyway, this example only require using symmetric to evaluate the integrals. This function, we are lucky. It is an odd function. This function satisfies this equation. Here, on this line, I demonstrate how the function satisfies this equation. And also, I plot the graph of the function here. Okay, this function is an odd function. Integral from -10 to +10 on this function is the net area of the shaded region here, Because the graph is symmetric about the origin of function. This shaded region, the area of this shaded region above x-axis is this area. And the area below the x-axis is this area. These two areas are equal. So therefore, net area of this shaded region is 0. And therefore, this integral is 0. Now, consider the integral in part C. The function in this integral has an absolute value of x. For a function with absolute value, it is impossible to find anti-derivative for this function. So, fundamental theorem of calculus cannot be directly applied to compute this integral. But anyway, this example only requires use symmetry to evaluate integrals. The function in this integral this time is an even function. The function satisfies this equation. Here, on this line, I show how the function satisfies the equation required by an even function. And also I plot the graph of the function here. The graph is symmetric about the y-axis. Okay, now this integral from -2 to 2. This integral is the net area of the region from -2 to 2. This region clearly is symmetric about y-axis. So net area of the region from -2 to 2 is equal to 2 times the net area of the region from 0 to 2. So we have this equation. This integral is equal to 2 times the integral from 0 to 2. Okay, integral from 0 to 2, x is between 0 and 2. Between 0 and 2, x is a positive number. So I can remove the absolute value here. Absolute value of a positive number is the number itself. So in this integral, directly remove the absolute value. Then I get this equation. Now, for this function, I can find anti-derivative for it. But anyway, let me split this integral into a difference by difference rule. Okay, now let me apply fundamental theorem to compute each of these two integrals. The first integral anti-derivative is x. Second integral, the function anti-derivative is this. Easy to tell. Okay. Now plug in 2 in x, plug in 0 in x. Then I get this equation. Calculator, this number is -4. So this integral or the net area of the shaded region is -4. Now, integral in D, okay, yeah, integral in D. Function complicated, so it is difficult to find anti-derivative for this function. So if you want to use fundamental theorem to compute this integral, difficult. Okay, but this function, we are lucky. This function is an off function. This function satisfies this equation. Okay, here I demonstrate how the function satisfies the equation of f of negative x is equal to negative f of x of function. And here is the graph of this function. Symmetric about the origin, the graph. Okay, now integral from -2 to 2 is the net area of the region from -2 to 2, between -2 and 2. The shaded region here. Because the curve symmetric about the origin, area above is equal to area below. Therefore, area above minus area below is 0. So this integral is 0. So if you use fundamental theorem to compute this integral, you need to find anti-derivative first. But that is difficult. But use symmetry, it's easy to tell this integral is 0. Okay. Topic 2 today, average function value. As a motivation, let me show you 2 examples. Example 1, if 5 people weigh 155, 143, 180, 105, and 123 pounds, respectively, then what is their average weight? The answer to this question is simple. Just add the weight of the people and then divide the sum by 5, the number of the people. Then we get the average weight is 141.2 pounds. Example 2. Suppose some mountain here, some mountain. Suppose some mountain has an elevation given by this function, where h means height or elevation, where h is measured in meters above the sea level, and x represents horizontal distance in miles. Now the question is, we don't consider the whole mountain. We only consider the portion of the mountain between A and B, between A and B. Now the question is, what is the average elevation of the mountain between A and B? Here I use F bar to denote the average elevation. Bar means average. To answer the question, between A and B, we evenly pick points. Say pick n points, evenly pick. Then at each point, we compute the elevation of the mountain by this function. Now we have n points, so we have n elevations. of the mountain. Okay, now take average on these n elevations. Take average on these n elevations. This average is roughly the average elevation of the mountain between A and B. Roughly, this is F bar. F bar is the average elevation of the mountain between A and B. It's easy to understand that more points that we pick, this average is more closer to F bar. Okay, now I increase n, the number of points, to infinity. Then this average will approach some number. The number is exactly F bar. So F bar, the average elevation of the mountain between A and B, is this limit, this limit. Okay, now in the following, let me write this limit into an integral. Chapter 5, this whole chapter is about integrals. Everything is integral. Now let me write this limit as an integral in the following. Okay. Okay. F bar is this limit. Let me write this quotient as 1 over n times this sum. Next, let me write 1 over n as 1 over b minus a times b minus a over n. B minus a, constant. So 1 over b minus a, constant. It doesn't depend on n. So I can move this number outside the limit to get this equation. What is b minus a divided by n? If we evenly cut the interval from a to b into n subintervals, then each subinterval, the length is b minus a divided by n. So the both use delta x. Delta x is the length of each subinterval. So b minus a over n is delta x, the length of each subinterval. Now I distribute delta x to all the terms in this sum to get this equation. Okay, now in this sum, the first term, delta x times function value at x1 star, it is the area of the first rectangle, right? Rectangle delta x is base of rectangle. Function value at x1 star, it is the height of rectangle. So this product is area of the first rectangle. And this is area of the second rectangle, and so on. This is area of the last rectangle. So actually this sum is sum of the areas of rectangles. Now take limit. N is the number of rectangles. That number of rectangles approach infinity. Then this sum will approach area of the region between A and B, and between the graph, the mountain surface curve and x-axis and the sea level, right? Okay, but anyway, limit of sum of areas of rectangles is integral by definition. So this limit is integral from a to b on the function f. So therefore, we have average elevation of the mountain is 1 over b minus a times integral from a to b on the elevation function f. But actually, this result can be extended to any function. Okay, now suppose f is a general function, not necessary to be the elevation of a mountain. Okay, then over this interval AB, the function has infinitely many function values. Okay, now the question is, what is the average of these infinitely many function values? Take an average on these infinitely many function values. The formula is, okay, f bar. By f bar, I mean average function value over this interval. Then f bar, the formula to compute f bar is 1 over b minus a times integral from a to b on the function f. So this formula, okay, is true not only for elevation function of a mountain, and also it is true for any function. If you want to find average function value of a general function on some interval AB, then the average is given by this integral. Now, in the following, let me show you examples about how to use this formula to solve problems. Two examples about this formula. The formula for the average function value. Example 1. Find the average value of the function x to the third on the interval -1 to 1. Here is a plot of the function. Between -1 and 1, this function has infinitely many function values. Now I want to take an average on these function values. The function has infinitely many function values, but those function values, they appear in pairs with opposite sides. For example, function value at 0.1 is 0.1 to the third. It is 0.001. Function value at -0.1 is -0.1 to the third. It is -0.001. These two function values are in one pair with opposite sides. One is positive, the other one is negative. Second example. Function value at 1/2 is 1/8. Function value at -1/2 is -1/8. These two function values are in one pair. The sides are opposite, positive 1/8, negative 1/8. So the function has infinitely many function values, but they appear in pairs with opposite sides. Because of this, then I guess the average of the function values, even though there are infinitely many function values, take average, then the average should be zero. Now let me use this formula to confirm my guess. F bar, the average function value by formula, it is 1 over b minus a times integral from a to b on the function. Now A is -1, B is 1. Okay. 1 over 1 minus -1 is 1/2. So we have this equation. To compute this integral, I use fundamental theorem of calculus. Find one anti-derivative for x to the third. It is 1/4 x to the fourth. Before I plug in 1 in x, -1 in x, let me simplify the coefficient. 1/2 times 1/4 is 1/8. Now, plug in 1 in x, plug in -1 in x, then make a difference. Okay, this number is 0. Yes, by formula, I get the average function value is 0. This confirms what I observe. My guess is 0. Yeah. Example 2. Average temperature. At the time T hours after room, the outdoor temperature is given by this function. Now, determine the average temperature for T between 0 and 3. 0, T is 0 corresponds to room. T is 3 corresponds to 3 p.m. So this question is determine the average temperature between room and 3 p.m. We have average function value formula. I use the formula. Then the average temperature is 1 over, by formula, 1 over b minus a times integral from a to b on the function, on the temperature function. Now b is 3, a is 0. Plug in 48 minus t squared into the function t. Then we have this equation. Split the integral into a difference of two integrals by difference formula. Now, to compute these two integrals, we can use fundamental theorem of calculus. The function in the first integral is 48. Anti-derivative is 48 times t. The function in the second integral is t squared. Anti-derivative for t squared is 1/3 t to the third. Okay, yeah, this step is fundamental theorem. Now, plug in the number 3 in t, plug in 0 in t, then we get this equation. Calculator, then we get 35. So between room and 3 p.m., the outdoor temperature, the average is 45 degrees.